Okay. And we have a quorum. All right. Welcome to Radio Telescope Observation Party for March 2025. Remember, you still want to get online for the Western Conference. I think it's too late. Tom has that. It's too late to sign up for in person, but I think you get online here for maybe the rest of the week. You can sign up for online. We will be publishing the proceedings after the conference. We've gone through a couple of years where we published proceedings before, and then we have all these revisions because people didn't have their talks ready until after the conference, but after the conference, then we revise it and resend it. So we just gave up all of that, and when we get all the actual presentations and papers and everything, which we'll have during the conference, we'll the next week produce proceedings and send that out. So that's going to work a little different than it has in the past, but it'll work. And I'm going to thank Jason, our VLA representative, for doing a lot to help that. And Ted and I will be sort of moderating the online, which means that that'll allow the people on site to go for lunch, for breaks and things like that. And Ted and I will just keep the conversation going for the online people. And then those guys will come back and they'll make their tours and all that kind of stuff. And we'll sort of keep the online going. Okay. So the online is pretty fun. Sort of a 2 full days of talk while the other guys are carousing around the VLA. Eastern Conference this year is going to be joint with Radio Jove. So you're going to see a lot of new Radio Jove stuff. People are going to set up Radio Jove in the behind the bunkhouse there, and so we'll get a lot of that. We haven't had a joint one since like 2017 or I think somewhere around there. So a lot of the same people, but we'll get that going. Okay. Tom, do you have anything for treasurer?
Well, yes, the in-person registration is closed. If you have not done it already, you will not be able to. And if I get any money sent directly from PayPal, I'm going to just kick it back to you. But I will still continue to accept online registrations probably through the middle of the day, call it noon Eastern time on the 12th of March. Something like that is probably what's going to happen. Other than that, not much to say. There have been a steady trickle of people memberships and have been a steady trickle of people signing up for the Western Conference. Let's see. I think the number is 17 people in person and about 40 people in total. So call it 30 people online so far. Anything else? Ask me questions and I'll try to answer them.
I'll just chime in real quick on the Western Conference. It is, I did find out that they do want visit requests for everybody. So I actually repeated the stuff I sent to Ken Redcap. I just put it in the message board, the chat. Yeah. So there's a link to the visit request site, and then I have some specific instructions on what people should put in the different fields so that they're not wondering how to fill it out. So definitely everybody that's planning on attending in person, please do this as soon as possible, because I'd like to make sure we have everybody completely everything sorted out well ahead of time. So, and I actually do personally get a notification from the security person once they have been processed, and I've already gotten a couple in. So, and I'll be keeping a running tally and kind of coordinating with Ken to reach out to people that haven't done it when we get closer to the time. So,
All right, great. And just emphasize the online people do not have to do that. That's
No,
correct. right?
no, it's just for coming on site into the
Right.
detox facility. So
Okay, excellent. Okay, one other initiative I am promoting at the moment, and you guys feel free to chime in or send, talk about the forum, etc. Is that we are our bylaws allow affiliate memberships, and I'm thinking about turning some of these large amateur observatories into affiliates. And that would be like Astropeiler, the DSES organization, and the VLA is a little too big, but it's, we might let them in if they really, fight for it. But also the one in Canada, there's a couple other ones that are amateur observatories that we've been, the people you recognize them immediately as people we've talked to a number of times. The one up at Ted's one, you always see, behind him, and that's Little Thompson Observatory. We did those, and potentially the positives for the observatory is that they may get a page of advertising in the journal. They would be allowed to use our SARA logo. We would allow maybe their members to come on the forum with us here. There's a couple other things we can do, which still has to be worked out. A positive for SARA members is that, like DSES, that's how I got into SARA, that advertised that those members didn't even know SARA existed. And then we went to the 2017 Western Conference, and then now almost everybody's a SARA member. Even though they currently are working day to day with the DSES observatory group, but they're SARA members in general. And that's the same with the Australia group they have a various organizations down there that and they have a big antenna farm that could be added. So we're and here comes Ray. Okay. So so I'm thinking about doing that. Details to be worked, but I think it's a win-win by adding these observatories, and we'll start seeing more interaction between the SARA and other groups. Okay, any comments first? And then I want to bring on Rick from DSCS. Rick, are you ready about your Earth, Venus, Earth experiment, or just part of it?
Yeah.
Okay,
Yeah.
go ahead.
The big new news is that our payload, which is interesting, high-powered 1296 megahertz payload, is ready, and it showed up at Haswell, and I have a couple of pictures to share. The first one is,
And by payload, you mean transmitter receiver combination up at the dish.
yeah, this is sort of what the payload looks like, and this will be mounted at the feed point of the dish. All of this. Well, all of this is a pair of 1200 watt 1296 power amplifiers that are combined to produce a minimum of 1500 watts key down for at least 5 minutes at a time or more, to generate the signals that we're going to send to Venus. And it includes the LNA and the transverter. Everything is going to be right there at the antenna feed, and I'm going to show you a picture of what it actually looks like as it was yesterday. This is the entire package. with power supplies, power amplifiers, LNAs, circulator to combine the 1200 watt outputs from the two amplifiers. What little coax cable there is, very short pieces up here just to hook modules together. There's no coax going down to the ground. There's no significant line losses. And even the antenna is attached to this package when it's installed. It's not shown here, but it's all one big package that mounts at the antenna feed. And as far as I know, it's up and running. And the only reason it's not in the feed yet is there's some mechanical issues of mounting it and protecting it from the weather. And in particular, it has to be mounted so when the antenna is pointed at the horizon or straight up and down, this 100-pound package will come loose and fall down. So the mechanical mounting is a big deal. And then one last quick picture. We have been working diligently on getting our networking in the new building established. And this is a picture of the Cat6 cables that we have wired everywhere. This is going to be the hub where everything comes in and gets jumpered to the various buildings and servers and the outside world. That little box on top is the thing our internet service provider gave us. And so we're trying to get this all wired up as quickly as we can. We also have, in addition to Cat6 cabling, we have what am I trying to say? We have fiber optics running up to the feed in the antenna, and that's controlling most of this EVE experiment. It's all fiber optics. And we also have two brand new runs of 220 volts, 20 amps, and another brand new run of 110 volts, 20 amps at the feed point in the antenna. So we had the electricians, and they had a good old time, great big man lift and everything to string all those wires. So we have plenty of power to run this new experiment. The fun thing will be when we're done with EVE, we will have a very powerful moon bounce signal for all your ham radio operators. That'll be leftover use for this. I expect the EVE project will have great deal of challenges, but whatever we learn from the experiments in the next month or two will be carried over to the next time that Venus is close to the Earth, and we will almost definitely run the EVE experiment again in another year and a half after this experiment with new and better ideas and science. We have science meetings on link budgets and all kinds of things every Wednesday at noon Mountain Time. And we have all the European partners. We have dishes, at least 2 60-foot and up dishes in Europe, at least 2 of them, and at least 1 on the East Coast in New Jersey that will all be participating in this Venus bounce project. So it's getting pretty exciting, but we're running out of time to get everything perfect. So cross your fingers. Oh, and while I've got the floor, I have two other things to tell you about. If any of you are ham radio operators, keep an eye out for QST in April. It's not published yet, but I've seen it. There will be a cover and an article that you will not want to miss. Trust me. My wife wrote it. I helped her, but she's the author. And it is a DSES article. It's about our recovering the 30-foot dish, which we hope to put back up in the air sometime this summer, maybe. And secondly, I will be teaching again this year, I discovered, at the International VLBI Symposium Technical Operations Workshop at Haystack Observatory the first full week of May of this year. So that's coming up pretty soon. I got to get my PowerPoint presentations finished, and it's already on the calendar. It'll be another hour and a half presentation given 2 or 3 times during the week on precision, time, and frequency, and why you need it for doing VLBI with radio telescopes. So that'll keep me busy for a while. And that's all I have.
Great. Any questions for Rick? Well, Ray, since we got you on, did you have anything you want to add? Okay, let's go Eastern time zone. Let's go for Eduard.
All right. Yeah. Good evening, everyone. So, yeah, I've a couple things to show still for my Extragalactic hydrogen project. Actually, the dish is now back in the shed because the weather was a little bit bad last week, but I still managed to collect a bunch of great data. Last weekend I also visited Astropeiler, did some water maser work together with Wolfgang. Maybe he will present something about that, maybe not. It was not terribly exciting actually, but we'll see. Anyway, okay, I think I'll share my presentation. Please share. Yeah. Okay, I hope you can see this, and I'm going to now put it in presenting mode. There we go. Okay, so yeah, over the past few meetings on the RTOP, I reported on the progress of my extragalactic hydrogen observations, in particular, the observations of Messier 31 and Messier 33. And I also mentioned that I was working on the detection of 2 other more distant and fainter galaxies. So these were IC 342 and Messier 101. But I also mentioned that I didn't have any definitive data yet. But yeah, today I actually have. So that's what I'm going to present. So yeah, if you look at my short list of galaxies that may or may not be detectable with any dish, so we can see Messier 31 and Messier 33 are the main ones that we can detect at 220 megahertz. So those are flux densities of 120 and 70 Jansky. So, and I've successfully observed both of them. And IC 342 is the next one down the list. It's about half as bright as Messier 33. And yeah, Messier 33 was already a little bit tricky, a little bit challenging. So IC 342 was going to be really quite a challenge. And yeah, go even further down the list, Messier 101 is even more difficult. It's again half as bright, so it's 4 times weaker than Messier 33. So this is really getting into territory where it gets a bit iffy if this like even possible at all with a 3-meter dish, but definitely requires quite some serious integration time. So yeah, I don't want to spend too much time explaining the setup all again, because I already did that in previous meetings. But yeah, here's just a very quick summary of it all. It's a 3-meter dish. I'm using a G8 FEK LNA, so it's not one of those how do you call those? Salbird H1 LNA, so it doesn't have a filter included, but it's quite good. So I have a separate filter, and then there's another amplifier to overcome the cable losses, and then I'm using an AirSpy Mini SDR with the SDR Sharp software and the IF Average plugin to collect my spectra. So I'm also not going to spend too much time explaining the methods, but the basic gist of it is that I'm using the drift scan methods. So because this dish is just stationary, it's not placed on the tracking mount. So what I just do is that I just point it at the declination of the target of interest. And then every day the target just passes through the beam as the Earth rotates. And yeah, I collect spectra before, during, and after the transit. And then I use the spectra collected before and after the transit to do the bandpass correction, to remove the bandpass ripple that is just inherent to the SDR and the system. So we can actually reveal the faint galaxy signal. Okay. If there are any questions about the methods, then please ask. Otherwise, I'm just going to continue. No questions? Right. Okay, so IC342. So this is a galaxy that is actually quite distant. It has a distance of about 10.7 million light years, which is quite a bit farther than Messier 31 and Messier 33, which are both at about a distance of 2.5 to 3 million light years in so-called local group. Sort of like the local galaxies around the Milky Way that are still gravitationally bound together. So IC342 is outside this local. It's not really gravitationally bound to our galaxy or to Messier 31 or Messier 33. So it's quite a bit more distant. And yeah, as you can see in the spectrum from a publication that I found from 1980s, you can see that the spectrum partially overlaps with the local hydrogen around 0 kilometers per second. So this makes it quite tricky to detect IC342, just apart from its like general like weakness of the signal. There is a part of the profile that stretches to about 130 kilometers per second that is outside of the range of the local hydrogen and should be in theory detectable. So I did some simulations using the lab survey to see if there was potential overlap with the local hydrogen, and there wasn't for the more redshifted part of the galaxy spectral profile. So this looked to be just about doable. So yeah, this after averaging 7 drift scans of this galaxy, my result didn't look terribly good. So there's one good thing about IC342, and that is located quite far to the north, not very far from the North Star, so or from the celestial pole. So the transit actually through the beam takes quite long. So I can collect about 40 minutes of useful data every day on this galaxy, compared to only 20 minutes for Messier 33, which is at a bit more southerly declination, a little bit closer to the right a bit closer to the celestial equator. Well, the bad thing about this is that actually I have a source of RFI interference to the north, and yeah, at the very low levels of signal that I'm dealing with these galaxies, that RFI, even a little bit of RFI can already make your observations really, really difficult. So you can see here that there's quite a bit of background slope still remaining in the spectrum, even after removing the before and after transit spectra. And you can also see all these negative spikes, which are caused by RFI interference, which was a little bit stronger in the pre and post transit reference spectra compared to the spectra recorded during the transit galaxy. So yeah, it's with this is something that can still be dealt with. So the first thing I did was that I fitted the trend line through the parts of the spectrum outside of the where I expected the galaxy signal to be and the local hydrogen. I didn't really bother with fitting a more complicated curve that would also flatten out the or blue shifted, so the negative velocity part of the spectrum, because that's not where the hydrogen emission of this galaxy is located. So I wasn't really interested in that part. So what I then did is that I just defined a threshold, essentially, and below which like the RFI spikes are located. So you see that over here. And then I just removed all the spectral bins where the amplitude value was below this threshold. So essentially this is removing these RFI spikes. And then our spectrum starts to look a little bit more clear. So we can actually start to see some sort of peak or some sort of plateau around 100 kilometers per second, which is approximately where we expect the signal of this galaxy to be. So yeah, and finally I reduced the spectral resolution to 35 kilohertz to get a little bit better signal to noise ratio, and I plotted this end result together with a simulated spectrum from the lab survey, just like I discussed in the previous Drinks Lounge, actually during my my presentation there. And you can see that indeed this peak at 100 kilometers per second and then the slope towards 130 kilometers per second matches up quite nicely with the lab survey simulation. So it looks like we actually managed to detect this galaxy, although still a little bit of uncertainty because yeah, there could still be like some RFI signal, but it would be I actually expect that this is actually the actual galaxy, because the velocity and the level also the brightness temperature really match up quite nicely. So then I also collected a bunch of transits of Messier 101. So this is an even more distant galaxy at 21 million light years, so it's well outside of the local group again. It has quite a high recession velocity, around 150 kilometers per second, so it's also well outside the local hydrogen emission. Also has a very nice double-horned spectral profile, which is very characteristic of these galaxies. Although we can see that the red-shifted horn is quite a bit brighter than the blue-shifted one. So yeah, after averaging all these spectra or all these results from all these transits, then this is the end result that I got. This time I didn't have to deal with any bad RFI, because when I'm pointing my dish towards Messier 101, it's pretty much right overhead, and I don't really pick up much RFI in that direction. So we can actually see that there is something of a peak at around 300 kilometers per second, and then there's a little plateau, and there's seems to be a little hump around 150-ish kilometers per second. So yeah, when we compare this to the lab survey simulation, we can see that this peak at 300 kilometers per second really matches up quite nicely with the blue shifted horn of this galaxy. And then the other, like the red shifted horn at around 200 kilometers per second, that's a little bit more uncertain, but yeah, I think yeah the level of the noise is just too high, and this is just too weak to really resolve. But I think at least I picked up the 300 kilometers per second peak. So this looks to be a rather marginal but still positive detection. So that was it for my part today. So if there are any questions, please ask. Thank you. That's great fun. I'm taking notes.
Yeah, great work.
I have a quick question. On these galaxies that appear to be pretty much face on, at least some of the optical pictures, just what component is associated with the blue shift? I can understand the red shift from a recession of the galaxy in relationship to the Milky Way, but what component produces the blue shift?
Great question, actually. So what's happening here is that these galaxies, they are rotating, and they are almost edge on in these cases, but not quite completely. So one side of the galaxy is still like spinning a little bit away from us. So we get a bit more redshift there, and the other side of the galaxy is still spinning a little bit more towards us. So we get a blue shift there. And then on top of that, there's also the general red or blue shift, depending on how fast the galaxy is actually moving as a whole with respect to us. Does this answer your question?
Well, I was just curious if they're face on. There must have some angular deviations from being perpendicular. Otherwise, I don't.
Yeah,
It's,
I think so.
I have a slide in my presentation that I'm going to give at the Western Conference that actually shows several examples of this and how the tilt affects the width of the profile. And M101 is fairly narrow because it is almost face on, but it's not exactly face on. It's at an angle of maybe like 60 degrees or something to us. So
yeah, that's what I meant. Indeed, like these galaxies, they look face on, but they're not exactly face on. So you still get random blue shifts. It's actually pretty rare. It has to be like coincidentally, like almost perfectly perpendicular to our line of sight in order to like not see any red or blue shifts due to the rotation.
yeah, I think the closest example to almost perfect face on, it would be M74. And when you look at spectral profile, there's a little tiny separation, but it's just almost just one peak. And so like you said, if it is actually perpendicular, it would be just one peak because they'd be on top of each other, right? Because the radial velocity from the spin would not exist. It would be completely 100% tangential. So,
well, that makes sense. Appreciate the explanations. Thank you.
All right, any more questions for Edward? Excellent work. You guys are really I haven't seen anybody else do Extragalactic, so you guys are really sort of setting the stage for a new amateur goal. Okay, let's get to Dimitri.
Hello to all. Glad to see you. Nice work, Edward, and nice work from Edward. Well, about the W49 measures for 3 observations. I'm preparing presentations for the Western Conference about W75N. Here is some message about part that I will not include in presentations. Just a moment. This is about estimation of measure telescope 6.7 gigahertz parameters. I do not include this in presentations. There is some math in this estimation, but some appendix in conference paper. I will prepare some appendix in conference paper about in text in conference paper about these estimations and would say now about problem estimations of these parameters. This small single dish, 2.4 meters, beamwidth about 1.3 degrees in for 6.7 gigahertz. The size of beam is comparable with sun angular size, and this is a problem when we need to estimate dish characteristic by sun radiation, and I will talk about the problem when the size of sun and size and beam size of dish are comparable. This is estimated parameters of my dish, 2.4 meters aperture efficiency, forward gain, dish sensitivity, also measured system temperature of this telescope, about 100 kelvins, and most important for measures observations, system equivalent flux density of the telescope. This system equivalent flux density define minimal detectable peak flux density for my case. This is about 80 Yansky for our resolution bandwidth, about 5 kilohertz and 1 hour of integrations, and this is minimal. Detectable peak flux density can be calculated from radiometer equation. This is radiometer equation for measure line, and SLD is needed for estimation of minimal peak flux density. So it's important for other estimation for all system sensitivity. Problem arises when the size of or BMS is comparable to the sun. We usually have known by measurements some flux density from working frequency, but well applicable formula for antenna temperature if uses a full flux from solar disk, and when the beam is light, this is all flux is received by peak of antenna beam, and when beam is narrow, some part of flux of solar flux is received with less less gain, and in beam slopes, it follows the formula for antenna, or will applicable formula for antenna temperature should be corrected for narrow beams. I used beam filling factor for this case. Filling of antenna beam by sun is small, is low. It's just one peak of the beam. For narrow beam, sun can feel the beam can feel the beam more, and when I use beam filling factors for this case, we have beam filling factors in this form. This is just general form of beam filling factors in common case for when beam wise is much bigger than size of sun, and corrections can be done if we divide this temperature by filling factors for wide beam and multiplying multiplying by general form of beam filling factors. Also, I include atmospheric continuation for the first estimation can be set by equal to unity to 1, and some flux density can be calculated from measurement data. I will talk about in the next slide. Also, antenna temperature can be obtained by measurements of sun radiations. Y factor is the ratio of receiver's output power when beam is directed and sees the sun, and when is somewhat moved from the sun outside the sun. This formula is used system temperature, and this antenna temperature should coincide with antenna temperature calculated from sun flux density. Sun flux density I usually obtain from near Mons solar observatory data. They give data for 5 gigahertz and 8.8 gigahertz and 6.7 gigahertz solar flux density can be obtained by interpolation. Solar flux unit, they give the data in solar flux units. This is units is bigger than Yansky, 10 intended for 10 and 4. Uh, uh, 10 and 4 force power and power force. This is all 5 units for sun. It's more convenient to for expressing solar flux densities very huge, and it is very huge. Resulting formulas for aperture efficiency, and dish sensitivity is rather big. Somewhat meticulous, but formula for system equilibrium flux densities is simpler, more simpler, can be used immediately for the calculations. Used immediately solar flux units from observations data. You need only to set beam filling factors, which using size of sun. The Y factor can be obtained from measurements. This is not CFD formula do not contain the system temperature, so you need not to measure system temperature separately, and CFD formula can be used immediately for calculations. Okay, thanks. If some questions, I will glad to answer.
Any questions for Dmitry? Go ahead, whoever that was.
Okay, thank you.
All right. Okay. Thanks, Dmitry. Andrew, I heard you had some troubleshooting success.
So I keep remembering to turn on my audio and video. Yeah, so thank you very much, and nice to meet everybody. I hope everyone's okay this week. Firstly, we got Jason online, haven't we? We do. I have a massive thank you to Jason to make here for the time that he's given me over the last couple of weeks. Without him, I wouldn't be able to have achieved what I have done. So basically, you'll see in a second. Essentially, I'll talk about it in a minute or two, and you'll see why. So, a number of people keep asking me how I've got on with the parabolic solar cooker dish and whether I've had any success with that. And the reality is, I had quite a lot of problems with it, getting it to get anything resembling a hydrogen trace, although it seemed to get a little bit of a hydrogen trace, which in a minute or two you'll see is really quite surprising given the problems that we found with the setup. Jason enough, it could get anything whatsoever, but nevertheless, but obviously many people are interested because it's quite cheap. I would just give one conclusion that I've made in all this business of doing the parabolic solar cooker, and this has got nothing to do with the problems that we're going to find tonight. And that is just to say that anyone that's considering buying one, I wouldn't bother. Go out and buy yourself a proper aluminium dish, for the simple reason that the parabolic dish from the solar cookers has two major problems with it. One is that it's made of light steel, so it rusts like mad. So if we're ever spending a fortune trying to paint it, and that's one of the things that I've been putting on the mailing list about asking about different types of paint. Well, by the time you add up all the cost of that, you may think, well, I may have gone and bought an aluminium one, which wouldn't have had the problems. The second thing is there's no, it's not the easiest thing in the world to actually attach to your mount. Whereas I'm assuming that a proper aluminium dish would actually have some bits at the back of it to attach to the mount much more easily. And secondly, probably much easier to find the focus point and actually attach some mechanism for holding your waveguide. Anyway, having said that, those aren't the things that were creating the issues for me. And I've got a little presentation that I put together, which I will show you all. Doesn't take very long, but hopefully it'll of interest to you. Where am I? Excuse me. It's there. Why can't I find it? Please just go for the screen. Very well. Can you see it saying Nano-VNA analysis of LRO H2? Has that appeared for everybody?
Looked great.
Marvelous, great. So Jason gave me 2 lots of 2 hours, which is marvelous, especially as they're straight after work when we've been working all day. So it was quite interesting because it was midnight here, my time, midnight to 2 a.m. And it was, it reminded me of sessions out with the telescope, the visual telescope. So it was actually quite fun, really, I would say. But anyway, so he got me to buy one of these things called a Nano-VNA vector network analyzer, which audio experts will probably know all about these things, but I'd never heard of one before. And I can tell you, if he hadn't walked me through it while holding my hand, there is no way I could have worked out how to use it because it was incredibly complicated. And what resembled instructions with it was about 2 short pages of I don't know what, but they certainly wouldn't have explained the complexity of trying to get this thing to work. But what I can say is if you haven't got one and your equipment is not working 100%, then buy one of these because they're only about 40 or 50 pounds and they are really impressive with what they'll achieve. So for those that don't know anything about it, I looked up a little bit about what they were just for my own benefit. I thought I'd share that with you a little bit. Hang on, this isn't moving. Why is it not moving to the next page? Here we are. So, sorry, start off with this one here. So why did Jason help me out with this? Well, because as I say, we weren't really detecting any signal of any meaning. Alex has pointed out to me before that my ptarmigan array isn't performing particularly well, but at least it allows me to map the Milky Way. And this one was not even achieving anything at all, given that it was about 3 times the surface area. It didn't make any sense, especially as it was set up next door to the other hydrogen scope, pointed in the same direction, and had actually, as far as I could tell, used the same equipment at the back to actually get it working with the same software. So it didn't really make any sense to me. So thanks, Jason, as I say. So that's just a picture, just to show you what these things look like. If you've ever seen them before, firstly, if you've never seen a sawbird, that's that little black thing on the left-hand side. Giveaways says sawbird on it, which is a filter of hydrogen line, 1420 megahertz. And it also got 2 amplifiers in series in it, so a cascaded amplifier. So it's really quite impressive little bit of kit. A few things it doesn't have. It's got no real protection from RFI. That case that's on it is just a plastic case. It doesn't actually earth anything. And secondly, it's not waterproof either. The Nano-VNA's got thing on the right-hand side, so about 50 pounds. If you go onto AliExpress or eBay, you see hundreds of these things being sold. But what was interesting is I bought off Amazon one, which was supposedly a different make from Jason's, but he had his in action at his side, and I had mine in action at my side. And when we started going through the menus, it turned out to be exactly the same machine, just with a slightly different case and slightly different labeling. So that was quite interesting. Probably all coming out the same factory, I presume. I found this graphic, which is supposed to show what Nano-VNAs do. In essence, they allow you to test networks. They're designed mainly for things like computer networks, but they can be used for our sort of equipment. And so this is my sort of slightly, in my own brain, trying to get to grips with what this thing does. So it's cheap, it's handheld, but very complicated. And if you don't, and unless you're an engineer, you need somebody to show you how to do it. This isn't really a question of looking it up online, unless you really got a load of engineering or physics knowledge. And it allows you to test the various bits of devices you've got across a range of frequencies. And what's really good about it is you can isolate the different components of your system and test them systematically one at a time to find where the problems are. And as we discovered, the problem with our systems is it's easy to think that this is a radio telescope, but in fact it's not. It's 5 or 6 components, or if you're the guys doing extragalactic work, about 400 different components, all attached together, and any one of them can cause problems, but there's no reason why, if you've got problems, it's just one. You might have them across a range of different issues. And especially if you don't have the skills and knowledge like me, you won't know where to start to try and sort it out. To be honest, I think it's probably easier being a doctor than it is trying to sort this stuff out. And of course, the Chinese are mass producing these things, so the quality control is pretty awful. That's why it's nice and cheap. But it does mean that it's so easy for any of your components not to be working very well, or whatever the product specification says. And I put down there, which to me is an important point, maybe it's not performing quite according to the product specification sheets, but really, is it performing to do what I need it to do? That's the question. And particularly with the filters, does that mean it's passing what I need it to pass in band, i.e. the 1420 megahertz signal? Is that getting through and not being chopped out? And is it actually successfully, on something like the New Elec, is it successfully filtering out the stuff out of band as well? So the first thing that Jason and I did was we tested my antenna, which is my homemade, a little bit of rubbish. I say you did use guidelines that came from this group, so you'll see in a second why that's a great thing, because actually this turned out to be performing very well. So the measurements that had been put on this mailing list sometime in the past were perfect. Gave it a nice, I can't remember, Jason, what was the performance on the antenna? Do you remember? I believe across the entire band, so a few megahertz on either side of 1420, it had a VISWAR measurement on below 1.5. I mean, it was 1.2-ish, something like that, which is excellent. I mean, it was very well matched. Yeah. So I can't remember who it was that put those measurements on our group in the past, but thank you very much to whoever it was for such excellent. Because I'm not understanding what makes these things tick. I literally just said X number of millimeters and I chopped it off at X number of millimeters, and that was it. And this was literally made from an old coffee tin and a paper clip. I wanted a bit of metal, so anyone thinks you have to go out and buy a special piece of copper, you don't, just a paper clip. But you do need one of these chassis connectors. In this case, I've used an N-type, so it less likely to break. But there it is, just sort of Walmart special, one of these coffee tins, or sort of like one of the sort of cafe style or size things. I think about 15 centimeters across the top, I think. So that's my waveguide. So, but then we used the NanoVNA to systematically go through the different components. In this case, the cable, the coax cable that I'd attached to the antenna, and then the Sawbird itself, and to see what problems we got, and found that there were problems with both of which were potentially damning for my ability to actually detect hydrogen. So if you look carefully, you'll see this isn't actually an original picture. I've faked it a little bit using Photoshop to try and give the impression of what we actually saw, mainly because I didn't take a picture at the time, which was a shame. But so this is Jason was telling me called, is it, what did you say it was called again, Jason? A suck out. Suck out, yeah. So it's that dip that you see in the middle there. If you look at it where the ones are, the yellow one, you see a U-bend that comes right down. So that is showing that it's performing very poorly at 1420 megahertz. I think what I've done on this graph is actually tried to show that, annotate it a bit. So that's if you look at the top where it says log mag 10 decibels, then it says slash 6.03 decibels. That was what I was actually getting, for 6.03 decibels. When we compared with Jason's, and he was getting something like 20 to 25 decibels.
Just very poor performance and losing it across that bit. In fact, he was up to 25. Yeah, 25 I think he had on his, yeah. So in fact, here's a picture that I managed to take off at the time showing Jason's own Sawbird that he checked. He's got this lovely flat profile at the top, and you can just about see in the sort of vague writing at the top, 25 decibels next to the log mag, 10 decibels. So that's, in a perfect world, what you'd expect. So I rummaged through my drawer and found I actually had 3 different spare Sawbirds. So I sat down and performed the same process yesterday with the NanoVNA to see how they performed. I thought I'd give an idea, A, whether my stuff was working, and B, what the variability was like across these devices. So that's number 1. And you can see there's a little bit of a dip, which you're going to come back to just in a minute or two. But if we actually get to the 1420 megahertz, we're actually still hitting 22 decibels. So I'd say not too bad on that. It's the yellow line that we're looking at predominantly here, in case you're wondering all the different lines all over the screen. It's the yellow line particularly, the one that says S21 log mag 10 decibels slash. And it's what's the white bit that's just after the slash that matters. Here's the second one, and you can see there's a bit of a stronger dip, again at the same position. But again, the performance at 1420 megahertz is still 21 decibels. And then I got this slightly strange trace on the third Sawbird, which I don't really quite understand. Seems to have dipped down a lot more earlier on. But again, well, this particular case, only performing at 14 decibels. So I presume that was a load of rubbish, that particular one. However, while other people have been talking a bit earlier on, I have been listening to you, but at the same time, I've also been running the Nano-VNA analysis again on these 2 Sawbirds, including this particular one. And that's the first one, 22 decibels, and the second one, 21 decibels. So what I don't quite understand is why second time round, the trace seems to be different. That doesn't make any sense to me. Maybe at the end, in a second or two, somebody might have some ideas. I don't know whether that's a feature of the Sawbird or the NanoVNA or what. Anyway, if that sounds a bad enough problem, it was nothing compared to the next one, which was the coaxial cable, which I think actually gave us a bit of a surprise, didn't it, Jason, this one? So I'm using KMR 400 cable, which is very similar to LMR 400. But first, initially, we thought maybe this was just a poor clone and was performing very poorly. But in fact, it performed reasonably well when we tested it with the NanoVNA. But as I put there, all our devices use SMA connectors. So what's to come next might be, some of you will know it, but some of you might not. And if not, it's time for a real warning about what might happen if you. I can see somebody nodding here. He knows exactly what's coming next. So the cable I bought had an N-type at one side and an SMA at the other side. And here's a little picky showing the different types of SMA connectors you can get. If you've never heard of it before, there's actually a second type called a reverse polarity SMA, which tend to be used in computer networks, so my son tells me. And the important point is the pin is on the other side. So it's on the female rather than on the male. And when we looked at my cable, it turned out that my coax had the end without a pin on the end of it, the reverse polarity SMA male. And I was plugging it into a device, the Neuralec, which had a standard SMA female on it. So, of course, there was no actual pin, central connector connection between the coax and the Neuralec. Hence why, as I say, I'm very surprised that we managed to detect any hydrogen at all. And it happened that in my box, I had a couple of reverse polarity SMA to SMA adapters. So I was able to use one of those and connect it. And immediately we went from minus 32 decibels to minus 2 decibels across the run. So it was an absolute dramatic improvement. So that's the warning. If you've never heard of it before, there's these things called reverse polarity SMA
connectors. And if you're buying either connectors, the reason I have some adapters is because in the past I've bought other adapters that turned out to be RP ones, creating problems. But if you're just buying them off place at Amazon or eBay or wherever, just double check what it is that you're buying. Likewise, if you're buying cable, double check what's actually on the end of it. It might not tell you. It'd probably just say SMA. So you need to look very carefully at the pictures and see if you can work out exactly what type of connector it is. So you might be aware that I have a couple of Chinese cavity filters. So I'd just be interested to see what happened when I added these into the arrangement in terms of the NanoVNA. So perhaps Jason can tell me. So you can see on the yellow line there that there's a much narrower line there, because this is 1,400 to 1,427. So it is narrower than before. I mean, they're slightly crenulated rather than straight line at the top, but it still gives us, well, it has reduced down to 16 decibels. The phase seems to be all over the place a bit, which I don't quite understand. But if we move to the next one, which is actually a much narrower filter, so this is 1418 to 1422. This has actually given us a very narrow filtering, but it has actually significantly affected the number of decibels coming out the end. Anyway, this is without any Chinese cavity filter on it. This is just the new elect back, at this time with a new elect Sawbird, and with the central connector actually being attached now. So it gives us a decent hydrogen response there. That's an easy call from Easy Radio Astronomy. And I have here got a little bit of a time lapse just over the last 24 hours or so, just to show us going through the Milky Way and back out. Okay, and here we are. That's the solar cooker. With anyone who's wondering why I've got a tiny bit of coax, which is LMR for 240, so there won't be much loss on that. It's just to take off any pressure off the Sawbird from that KMR 400 cable I got shoved on the end of it. Otherwise, it'll end up breaking the Sawbird connectors. And of course, I have covered that with something to stop water getting into it. Okay, thank you very much indeed. Any comments or thoughts? Be very welcome.
Just a question, Andrew. Do you use the cavity filter and the Sawbird in series, or do you use one or the other?
Well, for that analysis, it's apart from the two pictures that showed the cavity filter, everything else was just the Sawbird. But I have been using, in terms of data collection, I have been using one of the Chinese cavity filters in series.
Do you see any improvement in signal?
Possibly. Nothing that's so great or so much loss as to make that much of a difference that I, get much more detail on my graphs.
All right. Well, excellent work. And I think we all learned a lot about the, not only those SMA connectors, but the NanoVNA. How much should, so Jason, should we get the ones that are on the Amazon, or
That's where I got mine. It was like $50, and it was well worth the money. I mean, it
sounds like it.
Yeah.
Okay.
It's worth saying, sorry, that there are two types or two different price ranges on Amazon when you look. There's one that goes up to 1.5 gigahertz, and there's one that goes up to 6 gigahertz, which will cost another $30. In your case, probably another $30 from your side. So for hydrogen work, you don't need that. The 1.5 gigahertz ones works absolutely fine for the hydrogen line signals.
We're all going to do masers here pretty soon, so yeah, we need the high ones. Okay.
Just to mention just a comment, they make that VNA in a 4-inch screen as well, and if you're getting old and blind like me, it sometimes that 4 inches
little easier to mess with than the little 2.7 inch or whatever. So
Well,
just
yeah,
just a,
and I
just,
also, oh, sorry.
just a comment.
Yeah, I also found that there is, you can plug it into your laptop with the little micro USB connection. And actually, there's a couple of free software applications where you can actually display it and control it from your laptop if you want to do that as well. So,
And to make Jason's point even more important, I have here, I don't know if it shows up, one of these NanoVNA. This is the model that goes up to 6 gigahertz. And when I bought it, I made the mistake of not, I used it, I when it came in, I charged it up, and I turned it on, it worked, put it up, didn't use it for a couple of months. Then I went back to try to use it. And the thing with these NanoVNAs is that they have a touch screen in order to manipulate some of the readings. And in this particular one, I expired the return date, and the touch screen was out, which is a problem. I actually, in the car, I have a Prius that has also a dashboard touch screen. I had to replace that after a few years. These resistance type touch screens tend to do that. They go out. And so the software that Jason mentioned is the critical thing. I mean, you can still use it. You just can't use it in a portable situation. You have to have it plugged into your PC. And I believe one of the softwares is, I think one of them is called NanoVNA storage or something like that. And that's quite useful if you run into a problem where everything works just fine, except for the touch screen. So just something to be aware of.
All right, excellent. Well, Jason, let's go to you since we got you online.
yeah, so I in the chat, we've had some requests for if there's some maybe instructions or extra, help on how to use this thing. I think it might be useful I think I might spend some time putting together some tutorial videos going through some of the same things that I went through with Andrew, because I think it would be really helpful for a lot of the amateur community. Because, I'm an electrical engineer for my job, so I use these kind of things a lot. And sometimes you forget that if you haven't been exposed to that kind of equipment, it can be really confusing to learn how to use it, especially if you don't have anybody to assist you and you're just trying to make sense out of poorly written instructions or random stuff you can find on the internet. So I think I'm going to take that on as a project over the next month or so to try to put together a series of short tutorials on how to basically set it up and use it to do the kinds of measurements for the stuff we're trying to do. So stay tuned for that.
That will be a big help, because I try with my special antenna and I'm struggling a bit. So,
Yeah.
thanks,
Yeah,
Jason.
there's a lot of things that can cause complexity in this kind of amateur activity, because there's just so many moving parts, So I'm going to share my screen just for a second. Trying to think, okay, so I'm going to share this screen, and I'm just going to show you guys. Can you see my my screen here?
Yeah.
Okay, I'm going to move this over here. Okay. So so what I'm showing here, just to give you a little bit of a treat, I'm actually at my office at the Science Center at NRAO, and what I've got pulled up here is actual live, I've got a screen that shows live fringe data from each of the antennas in the array, and we're seeing this actually happening live right now. So so what I do for my job, I am actually in the team. I'm one of the small team of people that supports the maintenance and care of the samplers in the receiver system. So the digital samplers. And so what you're seeing here is a GUI that's been created to allow us to see the built-in test data coming from the samplers. And so in this case, I've got antenna EA9 selected, and I've got sampler 301, and I'm looking at, I've got the heatsink temperatures on the 3-bit and 8-bit samplers. I've got, the tick period, which is kind of like the time code. It's currently observing in 3-bit mode. And then this GUI right here is on the other end of that optical data stream. So what these samplers do is they take in the down-converted IF channels from the antenna, and they feed them into a digital sampler, and then they package all that data up in a certain kind of serial format on several parallel, each one has 3 parallel separate optical streams to allow the throughput, because back when they designed these, a single serial channel wasn't fast enough to do it in real time. So they split it up into 3 different streams. And so each of these 4 samplers on the antenna have 3 streams. And what you're seeing here is the deformatter on the other end. So in the control building where the WIDAR correlator is, the first thing that it hits on the WIDAR correlator is a board called the deformatter, and it takes those optical streams and converts them back into to digital streams on the copper, and then it sends them into the correlator boards to do all the magic to make the interferometry happen. And so and then over here, this GUI is actually it allows me to see the IF channel, the digitized IF data stream coming in real time. So what we're actually seeing the IF spectra, and it's in 3-bit observing mode right now. So there's actually 2 separate spectra, and they're apparently they usually set each one to a separate subband in the main band they're looking at to allow them to focus in on specific areas of the band. And so, so this allows me to see what's going on. And for instance, when the antenna team finishes servicing an antenna, or in the case of the last several weeks, we've been moving from A configuration to D configuration. So they've been moving systematically each couple antennas a day. And when they get them set up on the new pedestal in their new location, and they get them back checked out, and the LOIF team has finished their checkouts, then they give me a call, and I check out the samplers and make sure they're working. And sometimes they have to be reset, they have to be realigned, and make sure the IF streams look good. And then I call up the LOIF team again and say, okay, we're good to go, pass it back to you. And then they can finish up what they're doing and turn it over to operations to put it back into service. And so just thought you guys might like to see a little bit of what I actually do with this stuff during the day when I'm working. So, and I think, have I stopped sharing yet?
Yeah.
Okay.
So you have lots of numbers on there for lots of different antennas.
Yeah.
You're choosing number 9. So what's the ABCD?
Okay. So yeah.
Spectrum?
And the short answer is each antenna has 4 separate IF streams, 2 for left-hand polarization and 2 for right-hand polarization. And that allows them flexibility to do different kinds of things with their observing. So it just gives them more options, I guess. So instead of just having 1 left and 1 right, they actually have 2 left and 2 right channels. And it gets even more complicated in 3-bit mode, because they actually can separate each of those channels into 2 subbands. And so you have even more. You can have up to, let's see, you can have up to 8 different channels going at the same time. So,
Okay, thank you. I'll say I understand.
one of the things that I'm gonna make sure that everybody attending both in person and remote to the conference, I'm going to make available PDF copies of the whole system block diagram, both for the antenna and for the correlator system. And so you can actually see a breakdown of the whole system and how the signal flow goes through it. And the cool thing about working at an RIO is, as opposed to, working for the Defense Department, is that the stuff that we're working on is public access. The information is not restricted. And so anybody can have a copy of the block diagram and see what's inside the receiver. And I think, I would imagine that lots of our members would just really appreciate and get a kick out of that. So I'm definitely going to make that happen. And also, if anyone attending in person is interested in like a large, like an e-size hard copy, like an actual paper copy, we should probably prepare ahead of time, but I can make that happen. So let me know if you might be interested in that, and I'll try to see what I can do, because it's the amount of information that's available to us on this system, because it is an open public asset, is just amazing. And I think you guys would just really enjoy looking at that. So I know I still do. I walk down in the hall all the time looking up at and just standing in front of the block diagram, just kind of looking at stuff,
I have one question for you. I
Yeah.
assume they made it 3 bits to get more bandwidth. What is the total bandwidth that you're pulling down?
So the 3-bit samplers have a sample rate of, let me pull it. It's just over 4 gigabits per second. So that's kind of the bandwidth limit. You have to be less than that. The interesting thing is they're sampling in the second Nyquist zone. So, which is interesting. Now that may be, gibberish to some of you, but, for me, when I first looked at the block diagram, I was scratching my head because I was like, wait, the IF frequency is the same as the sample rate. How does that work? And then I realized they were using second Nyquist zone, and they just band limit it so that it doesn't have aliasing problems. So,
Interesting.
and it's because when they built these samplers, that was as fast as they could go. So they just had to make it work. Right. We got a lot higher samplers now. So if in the future, as it appears that the next gen is going to be pushed out indefinitely in schedule, we got to keep these existing samplers operating for a lot longer than we intended. And my prediction is that a redesign of that subsystem is going to be happening sometime, because these things are getting to end of life and they're needing to be refreshed, let's say. So,
Well, the 4 gig is a pretty nice sample rate to have to be worrying about. If you upgraded, then you have to have everything else has to be faster to handle increased data too. So
yeah,
makes it
that is true. Now the 8-bit sample rate is half of that. It's like just over 2 gig. So, and that's why they still like to use the 3-bit sample mode, even though it's lower resolution, because it gives them much wider bandwidth and they can do other things with it. That's used. The science crew definitely makes use of that. So, okay. Yeah.
All right. Thanks, everybody. Or thanks to Jason. And we got a half hour left. So unless somebody else has a large presentation, let's just go quickly through some updates from other people. I'm just going to go down the list. Ted.
Just playing with Ezra, trying to see if we could do external galaxies. How could I push that into Ezra? And some little tweaks on other software. So pushing away, nothing else.
Okay, thanks. Jack Lobinger.
Just making sure I'm ready to head west here to go to the conference, and looking forward to seeing everybody.
All right. Got Osmar.
I'm here. Okay, just enjoying the talks today. Great talks.
I'm sorry. I saw the last name. I thought it was a German person or something. All right. Thanks. Jon Richards.
I have nothing to report.
Nothing? Okay. Jack.
Yeah, I'm continuing to take data with the H-line 3D stuff per Alex's design. That's using the Disky antenna. And to go to Andrew's point about the VNA, I mean, when I built this thing, I used the VNA and found that the center frequency that with the 1420 I was aiming for was a little bit off. It was about 3 dB down. So with the VNA, it was very easy to tune the antenna and get spot on. So I agree with the comments here. Yeah, I am an EE or a retired EE, but I figure once you're an engineer, you're an engineer till you're in the grave. But I think these are very inexpensive. I get the $125 one with the bigger screen, and it's worth every penny.
Okay. You got any video or photos of any of that stuff? Or
sure. Let's see if I can figure out how to share the screen. Let's see.
Let's go to the bottom. There you go.
So hopefully that's come up. Do you see that? Okay. That is some of my hydrogen data from a day of sampling. And this is using the Rhine-Arn free graphical software to process it. And I've used one of my equatorial mounts for my telescopes just to aim the things. I know that it's aimed exactly at where I expect Cygnus to be at a particular time of day. And sure enough, if you look at it, Cygnus has a right ascension of about 20.5, and that puts it right about here. And so sure enough, that's where Cygnus is coming through the display. And that's it for me. I don't know.
Good job.
I don't know how to unshare it. I'm afraid.
Oh, I could do that for you.
Okay, thank you.
I think. There you go. Great. Let's see. Johnny Cox.
Trying to get off. I don't have anything to present. I'm looking forward to the Eastern Conference, and I enjoyed all the talks. Thank you.
All right, great. Bob Strickland.
No, nothing new for me today, Rich.
Now, is this is it Michelle or Michael, or how do I pronounce that? Sappher?
You can call me Mike, Michael, Michel. In French, it's Michel, but Mike is as good. So
Now,
hello, everybody.
Are you actually?
I'm new guy. I have a little presentation, Rich, to just present what I'm doing. Can you see the presentation?
There it goes. Yep.
Okay. Sorry.
We currently see the slides down the left-hand side.
Sorry.
You might be able to just hit your space bar and have it advance if that's what you're trying to do.
Yeah. Okay.
It worked. It went to the next slide.
Sorry, guys. Okay, so my background, I am a retired engineer. I used to work in the nuclear industry and then in the electronic components industry. I'm an astronomer amateur for some years. I started with astrophotography and as many of you guys, and I have a Celestron C8. So I made pictures, and I wanted to make more science, so I made some exoplanet transit, making some photometry, which was very interesting. It's very nice to see that you can see exoplanet with a C8 in your garden. So it's very encouraged. The problem we had is that in France, especially where I live close to Paris, the weather is getting very, very, very bad. We have more and more days of fog and rain. So I thought, what can I do? Because I'm very attracted by astronomy and science. So I did start to explore radio astronomy, starting with I discovered that we can capture the satellites, NOAA satellite pictures. So that was my start, discovering SDR antenna, etc. So I have no background in radio waves, etc. So I have to learn everything. Then I discovered your site, the SARA group. I looked at many of your YouTube channel video, which I look at all your lessons, how to understand. And then I look at your conference. I say I should join this group. And so I start to equip myself. And thanks to Cline software, I started to really dig in all this. So my installation is rather simple. I have a grid, a Wi-Fi grid, which I equipped with 1.4 gig space boom from Welec, an LNR filter subbird, and external supply. I did struggle a bit about BST feeding or external feeding, so I found the best was to use external feeding and a DC block. So I'm sure that no power comes from the SDR. And I did equip it with a Raspberry Pi 4. The nice thing about it is you don't have to have the window open all the night in winter to get the signal to your PC. So I figured out I could put all this on the Raspberry Pi. And I start, of course, in the Raspberry Pi, I have Wi-Fi, which is connected to my internal Wi-Fi. But I didn't realize when I start the Wi-Fi would perturb the signals. I had to put a 10-meter coax and put the Raspberry Pi behind the concrete wall because it was perturbating. So now it works. And thanks to Ed, easier software, I could start it. So far I've been, it's not 162, it's 62 drift scan. In fact, 122 is the file, but I make 2 files per day. So that's about 62 files I've done so far. And 170,000 samples. Here you can see some results. So you can see that we can have the nice bump where it should be. So that's good. And the dots are not fully aligned with the galactic plane because I'm struggling a bit with the wind. And sometimes I have to realign my antenna because we have sometimes a lot of wind here. So you can see that the dots are not exactly all in the galactic plane. But here you can see that we have a nice view of the galaxy. And here I can start to have some arms visible. I can see one arm and the second one. So it's very exciting only to be able to see that. Here you see, I try to put that superposition with the image of our galaxy. So can figure out we see some more arm. And here you can see some result also where I'm quite happy with that because following TED rules to try to take out all the spike, I was able to get the maximum speed on the galaxy clouds at 236 kilometers, which is not far from the theoretical one, and get about the mass, confirm the mass of the galaxy. So I'm quite proud with this result. And I went through the RENA Graph 3D to make some nice 3D pictures. So here you can see one cat, one observation, one day observation. On this one on the side you see the galaxy, and here you have the 3D of the galaxy hours, which is of course to be improved. And currently I have some issue I need to solve. One of the major issue I have is that I have, if you look at this picture, so maybe I can have from time to time cuts in the signal, so brutal shot in the signal, which I am not really able to explain. It did improve a bit thanks to TED advice. I did tied up all the cables because they were loose, and with the wind, I think it explained a bit part of the problem I had, but still have to investigate on this. Also, I have to work on the galactic cross section, understand better to make it, which is not yet mastered, and so my next step is to improve. And I did try to make an antenna with LXPT. I tried to improve with LXPT advice on putting some, how you say, grid around and protect better the antenna. Also, I did design a dedicated boom according to his design, which was not very successful. I listened to Andrew because I may need to make better investigation with micro-VNA. I have one, but of course I know Jason, I need your I will need your tutorial to better understand how to improve my antenna. And of course I'll continue to accumulate data, continue drift scan. And outside that, I would like also to start to explore outside the hydrogen. But I know with my small antenna, I cannot dream to do much better. So I need your advice. That's it.
I have a comment. If you could go back to your very first slide.
Yes.
Maybe not the title, but I want to see the antenna. We need Alex for this, for an authority. In the top right-hand corner, is that picture of your antenna?
Yes,
Just a pretty
that's
picture.
mine. Yes, that's.
I wonder about the assembly. We have two choices to make.
No, sorry, this one is not my antenna. It's I took but on polarization. I did put it on the correct side. That means that it's on the small. On perpendicular to this one. So this one is not representative to mine. This one
my comment
should not work.
My comment
You
to
are right.
You can have that little bent metal piece either flaring away from the antenna or flaring to. I think we agree it should flare to the antenna, pointing down at the antenna surface. And the other way is, should it be upright or left and right? Up and down or left and right? And we think it's up and down. And I keep seeing pictures where they sell them with the wrong picture.
This is the picture from the internet, from Amazon, but mine I did oriented because I listened very carefully. I oriented it vertically, So it's on the direction of the small size of the antenna. But
Well, we're very impressed that you listen before you talk and discuss. So thank you.
but I still I put it with the shape towards the antenna, not out externally. So I think it's the proper. I'm not sure. Anyway, for anyone who wants to try with Raspberry Pi, be careful that the Wi-Fi from Raspberry Pi doesn't be collected by your antenna, so you have to put it rather far away. And myself, I did put that behind a concrete wall, so I'm sure it doesn't perturb too much, because problem I have is that in Paris area, we have a lot of interference and perturbation. It's rather noisy in the area, so I struggle. By the way, just that you can see that it's currently what I'm receiving. So you see that I've quite significant noise and peaks around, so it's not really easy.
I'm Michelle, Andrew here. So the question that Ted asked there, if you just unshare, I'd just like to share a graphic if that's okay.
Yeah. Let me check that I
yeah.
It's okay.
So
Thank you.
Question of orientation.
Yeah.
So that's the correct orientation then.
Okay. That's what I've done. That's what I have done.
Yeah. And it should be the long axis of your dish should be aimed east-west, because then you get the resolution of the long axis.
Yeah. That's great.
Yeah. I've put in the in the chat that the British Astronomical Association Radio Astronomy Group is setting up a new hydrogen line group, which is mainly aimed at beginners, but anybody is welcome to join. And we'd love to invite members of SARA or anybody else that'd like to join us. Really, you don't have to be a member of the British Astronomical Association Radio Astronomy Group to do so. And I put the first date as the 17th of March there at 7 p.m. UTC. So if anybody would like to join yourself, very much, I put my email address. Please drop me an email and I'll send you a link. And also, Michelle, being that you're relatively local to me, I'm in the UK. It might be that you and I want to have a bit more chat about.
Exactly. I would be very happy. It's more easy because we are on the right in the time zone, which is rather close.
Yeah. Well, I'm another protege of Ted's. Also use Easy Radio Astronomy. So perhaps
we are the fan.
My website address there as well. There's some interesting stuff on there you might want to look at.
Okay, so that's all for me.
Okay. Thanks for work. All right, let's keep going. Tom Fulton.
Yes, hello. Great talk as usual. Thank you for all of this information. I did want to just mention briefly. I want to thank Andrew or Andy. I'm not sure which you prefer, but he kindly accepted the request to work with me on following up regarding the Meteor radio scatter detection presentation he showed us on January 6th. So he's going to be working with me in a couple weeks to spend a couple hours to help me out with that. So thank you, sir. Truly appreciate it. Looking forward to it. Yeah, that's it.
Great. Thanks, everybody. Stanley.
Quick question. I'm sorry, Tom. For meteor detection, what signal are you using to reflect off meteors?
Well, I'm going to have to ask Andrew that.
Well, you're not located in the UK, so we're gonna. I don't know. It's we're gonna have to try and get some advice from people here about the best ones for you to go for.
Yeah,
My
We used to have
is the
we
least,
used to have-
but here at LTO in Colorado, we're using the TV digital transmitter of channel 2, whatever that is in RF, or around 54 megahertz. Good luck.
Sounds like we need to get Ted to join us in that meeting.
Well, if you're lucky enough to have a 2 or even a 6 channel where they're sort of in the VHF range, and unfortunately my area I'm not. We used to have the space fence, which is fantastic. The one that worked at 220 megahertz, and that got taken down. The Navaspar signal, and that one's gone. And so the only thing you can do that I've heard is using the pilot frequency for TV channels, because of the digital signal on TV channels is just a huge mess, and the only thing that's even a little spike is the pilot signal. But I'm just curious because I'm interested in the meteor scatter, and it's just to either that or find a far sort of intermediate range FN station or something you can latch onto over the horizon. But these are problems here in the U.S. that.
Andrew, in Europe, you have the Grave radar from the French. You are aware of the French radar. Grave radar is a very powerful radar to transmit satellites, and you can, from UK, you can receive it, because I saw some guys in UK are using it.
I'm in Southern California, so there's no way.
It's clear. I'll talk for European guys. For Europe, it's very, very powerful radar.
We do have a working group, and I got to get them back online to have SARA put together some beacons at 54 or 55 megahertz that we can use for meteor scatter. So we've got a group that's looking at that. I think they're stalled at the moment, but if anybody wants to be a beacon owner and specifically be the beacon for meteor scatter in the U.S., it's illegal to put a beacon up at that frequency, and we just need to coordinate it.
Rich, if I could add on that, SARA now has access to 2 1,000 watt transmitters. We're looking for a legal way to put those on the air to duplicate what both the UK and Belgian amateurs have done for meteor scatter. Chip Suffici and I have been working on a way to get a special scientific research license from the FCC to go full power with 1,000 watts on those transmitters. Currently, if we put them on the air, we would be limited by the amateur radio 100 watt limit. So we're looking into that. We're looking also at the modulation profile that we would use. Our preference, I believe, at this point would be to put out a solid unmodulated carrier that would probably give a better reflection profile. So I would say if anybody in this group would like to work with Chip, I think Charles Osborne, Mike Otte, and a couple others have expressed interest. We'd love to work with you. We have some equipment. Again, it's rather substantial, the equipment we have on hand. We just need brain power and somebody with the push to go ahead and move ahead. But I would say, looking around the world, if we could duplicate in North America what our friends in Europe have done, primarily with the Belgian system, I think that would give us a replacement for the diminishing FM or TV broadcast carriers.
So I would be happy. I'm in Northern California, but I have the passion and the ability to participate, but I don't have the expertise. So I'm happy to help any way I can. So it sounds like what I'm understanding is maybe, Andrew, what you mentioned that you're using the Graves system in Europe, and you're using passive radar at 143.048 megahertz. So it sounds like what the team's discussing here is maybe an equivalent to what is being offered. Is that kind of what's being discussed here?
Yes.
Okay.
Thank you.
Sorry, Rich. Tom, Ted and I are staying on line on after this meeting for a chat. If you want to, by all means, stay on a little bit and stay with us. And if there's anybody else who'd like to join us as well, and you can pick their brains a bit about meteor scatter up there in Northern America.
Thank you.
Okay. The after chat party. All right. Anybody else have anything significant? We only got a couple minutes left.
I could talk a little bit there.
Go for it.
Okay, thanks. Fascinating projects. Great to hear everything. Just wanted to say thanks to Alex Pettit for giving me some advice on the hydrogen Yagi that I've been working on for quite a while. And then also just share a few pictures here very, very briefly. Let's see if we can get that going. Okay. I just have a couple of pictures to show you and maybe a little bit of a story. This was a NASA observatory radio telescope it's near Ottawa. It's called Carp, Ontario. And it was going to be scrapped. And the guy who had the contract to maintain it found out about that. And he looked over the property and everything and ended up buying it. And then he reached out to a local astronomy club. This is kind of a great story because it saved the telescope. And they said, because he was just going to scrap the telescope and use the building. And they said, well, why don't you check with these guys, the Canadian Center for Experimental Radio Astronomy. And so they got together and they have a kind of made of an agreement that they could do their research here on this radio telescope, which was saved. So here's a picture of the dome. It's actually in a dome. So you got a really great scope for them to use, a radio telescope for them to use. So I was really, I found this paper and I thought, this is kind of neat because I'm interested in whisper and ham radio and that. But I wasn't familiar with all the reverse, okay, so they're talking about large scale traveling ionospheric disturbances and detecting those with radio amateur equipment, essentially. What we had in terms of the beacon network, the reverse beacon network, the weak signal propagation reporter network, the WhisperNet, of course. And then there's two other ones that I wasn't familiar with. So what they're looking at is using amateur radio data to provide a new method for studying the LSTIDs and HF communication impacts, essentially. So this I thought was really fascinating. And they published this, it's not that long ago. And I've been really interested in getting a whispered beacon up and running. So I found one. Let's see, where is it here? I think it's right here. It's kind of hidden underneath there. Can you get to that guy? Oh, it's because the menu's in the way. So if I just change the menu there. I don't know, where is it? Well, anyways, it's the small unit. It's made by Zactec, and this company's in Sweden, I believe. And it's a nice unit. It's very portable. It's packaged nicely. It's got the wide band, so you've got all the channels essentially across the band. It has a great interface in terms of software. It also has interface. The software is available online. So, I have a Linux system and I wasn't able to install the software, but I was able to download the HTML code and actually be able to program it directly through the USB. Okay. And that's that part of it. And then this part here, I thought people would be fascinated. I was working on a paper and I had to collect, sort of mine some data. And, it was May 11th, actually, it was my birthday, and it was amazing summer. And we actually saw the Aurora Borealis. We're in Northern Ontario, just about 5 hours north of Toronto, where we had a spectacular display. But while I was collecting the data, I noticed this huge drop, I collected this from Finland, actually, the Ulo, that's the University of Ulo. A friend of mine, his cousin actually works there. He was from Sudbury.
but this is the neutron monitor, so cosmic ray monitor. And you can see that during the year, whenever there's a drop, you're getting a Forbush decrease, which is, Scott Forbush was the U.S. physicist who discovered this effect and named after him. And you see the solar storm around May 11th, and this G5 storm hit. And look at the drop. It just plummeted. The cosmic rays plummeted because the ionosphere was so charged that it was blocking this cosmic ray. And what's very interesting about this one, and I've seen another paper from a Greek scientist who said that this was an abnormally long Forbush decrease. And you could see how long it took actually to recover from May the 11th right up to July the 5th. So you're talking a long time before it actually recovered back. And so that was sort of a kind of a something that came out of something else. I was just looking at 4 specific dates, and suddenly I noticed this part, and I thought, well, I better mention that part about it. But yeah, so that's everything I've been sort of looking at in terms of radio astronomy in the last little while, looking at the ionosphere a lot.
Great. Good work, Stanley. That's
okay.
Let's see. Only got a few more minutes. Rod?
Oh, no, thanks. Yeah, thanks. Just first time in a long time, working on a 3-meter dish and motorizing it for galactic mapping. So just tuning in. Great to see everybody.
Great, thanks. JB. No. Okay. Nis Holmes.
I don't know if you can hear me. Can you?
I can hear you.
Okay, great. Yeah, I'm listening here and enjoying all your presentations. Right now, I have no hardware, but I'm hoping my background in satellite communications and astronomy could sort of edge me into this field. But enjoying all the presentations, fantastic. I don't know if anybody saw my note, but one thing that really piqued my interest in your presentation today was Andrew with his coffee can feed. I used the same thing over 40 years ago to steal over-the-air cable TV. Exact same thing. Fantastic. It shows you technology can change, and sometimes it can change. So thank you, everybody.
All right. Okay. Anybody on this? Okay. I'm going to thanks everybody for our next meeting is in 2 weeks. It'll be Drake's Lounge. If you're not getting the notices, that means you're probably not an active member on our website. So if you want to become a member and get all these notices, go to the SARA webpage, go to the store, and sign in to be a new member for $20 for a year. Okay. Thanks, everybody. I'll leave this on for anybody who wants to talk after chat, which won't be recorded. And
hey, Rich.
Yeah, go ahead, Jason.
2 weeks is the SARA, is the Western Conference.
Oh, that always happens. Okay.
So you are going to actually be out at the VLA that day. So,
okay. So in 2 weeks, it'll be the Western Conference online. So we will not have this, but unless you're online, we'll be running that. Okay. Thanks, everybody.